Hello, everyone. Welcome to the final papers session for ICCP. My name is Matthew O'Toole, and I'll be your session chair. We have 4 great papers lined up. These papers are all about modeling and analyzing the physics of light in order to see around corners, see through skin, synthesize atmospheric turbulence, and recover reflectance functions. But before we start, I want to remind everyone that you can ask questions in the chat during the talk, and I'll relay these questions to the authors at the end of each talk. I'd also like to remind everyone to be part of ICCP's virtual group photo. So ICCP has a tradition of all attendees coming together at the end of the conference to capture a group photo to commemorate the event. This year, we'll do this by basically creating a virtual group photo by taking selfies and uploading them via the ICCP website. The deadline to do this is at 3:30 p.m. Central Time. That's the end of this session. So make sure that if you haven't done so, take a selfie now and upload your photo to the website. Now, let's get started with the first paper titled The Role of Wigner Distribution Function in Non-Lanocyte Imaging. The presenter is Xiaocheng Liu from the University of Wisconsin-Madison. Take it away.
Hello, everyone. This is Xiaocheng Liu from University of Wisconsin-Madison. This is a paper I co-authored with my advisor, Andreas Welton, who is now a professor at the Computational Optics group in Madison. This talk is about our recent work in non-lanocyte imaging. Overall, it tries to use Wigner distribution function to explain non-lanocyte imaging. For those of you who haven't heard non-lanocyte imaging, don't worry. Let's have a quick review on what is non-lanocyte imaging. The overall goal for non-lanocyte imaging is to use capture signals with design algorithm to take a hidden photo that is beyond human vision. First, people perform experiment remotely. We shoot a pulse laser from the hardware. Notice that this pulse laser have 70 picosecond temporal resolution, which is equivalent to a 2 cm light pulse traveling in air. This short laser pulse traveling through the scene and hit the wall, which is in the line of sight area. Once it hit the wall, the light will scatter everywhere in the room, which is invisible to us who perform the experiment. Notice that those scattered light will again hit the target, and the target reflect light back on the wall. Next, we have another focus detector on the wall, which can collect those reflected light. Currently, the most popular one we use to detecting those reflected light is called single photon avalanche diode, which is known as SPAT detector. Finally, we acquire some signals at different focus detector points and process them through computational algorithms. So, how does the capture signal look like? First, we need to understand if there's no light, there's no returning reflective photon. So we need at least one laser point on the wall. Then, with multiple detector points, we can acquire a spatial-like signal inside the detection area. Here are the capture signals reorganized in space X and Y and time dimension, which is just like a spatial temporal cube. There are many names and inverse methods that are associated with non-lanocyte imaging. In this talk, we focus on the phasor field non-lanocyte imaging. What is phasor field? A very simple way to show this is as following. For each capture signal in time, if one applies a one-dimensional Fourier transform, then we have shown that those capture signals in frequency are equivalent to the wavefront that exists at the aperture of regular optical imaging system. They just pretty much look like water ripple one can simply observe in daily life. So given the underlying wave nature, that's why we name it as phasor field method. Since it is a virtual wave on top of optic wave, we also name it as a virtual wave. Since it behaves like a wave, we can use a similar tool in wave optic, followed by the Fourier imaging principle, to describe the phasor field propagation. So now one can understand that the signals that are captured on the wall are some diffraction pattern. Then, to reconstruct a hidden scene, we have to propagate this wavefront back into the scene to form a hidden image. So what kinds of propagation that are suitable for describing this diffraction process. Let's now have a closer look on the diffraction propagation model that is being used. Given the input and output field on the plane in Cartesian coordinate, we can describe the output y as the convolution between the input field x with some convolution kernel h. In the null-side case, this h looks like this. In fact, this diffraction is called Rayleigh-Sommerfeld diffraction. Notice that the Rayleigh-Sommerfeld diffraction applies to all wave components inside the capture frequency cube. You can form a simple image using single frequency instead of frequency cube. This will look like someone is trying to do a refocusing around the corner. Overall, once you capture wavefront on the wall, then the phaser field guides us to use diffractive imaging method to perform reconstruction. If the null-side imaging problem can be treated like a regular Fourier optic problem, then what we can learn from the past work in image society. For this paper, we have shown how the Wigner distribution function is being used to describe the null-side imaging problem. So to do that, let's first review some basic principles about the Wigner distribution function. So first, if you know the Fourier transform, you should know that given the input signal, you can find the corresponding pair in the Fourier domain using the Fourier transform. It just behaves like a mapping that maps those two functions. The Wigner distribution function in a way that is similar to the Fourier transform, but it transforms the signal into a two-dimensional representation. So let's have a closer look on what is Wigner distribution function. The Wigner distribution function for the function f has three components in the labeling. The symbol f, which means that it is the Wigner distribution function for the object function f. Other two components are spatial variable x and spatial frequency variable mu. Here I use the term spatial and spatial frequency since it helps us to remind the physical meaning for the signal that we want to describe later on. So here is the specific definition of Wigner distribution function. So one can apply this and then you can calculate the corresponding output given the input. Okay, let's now have a detailed look on the wave imaging part. Most of the image formation model can be described by a linear integral. Mathematically, this means that once given an image application, the input function and output function are linked through a linear integral function. For most of imaging applications, this integral function is usually in either convolutional format or in a Fourier transform format. Just for a quick reminder, the null-side phaser field diffraction we just talked about a couple minutes ago fit perfectly into the convolution category. Okay, we have finished two parts. Let's see how the wave imaging intersect with the Wigner distribution function. Since we know that the wave imaging can be fundamentally described by a linear integral equation, and we also know how input-output signal transform in the Wigner distribution domain, the only thing for the next step is to find the relationship between input and output signal in the Wigner distribution domain. So given by the great mathematician, it's easy to show the following integral must be true in the Wigner distribution domain. Similar to the H used in a standard description, we can describe this linear process in the Wigner distribution domain as long as we have this capital K kernel K. But how we know capital K? There must be a connection between H and K, right? Well, the answer is yes. Once you know integral kernel H, you can use a formula that is shown here to calculate the capital K. So to put this as a simple English, as long as you know how to formulate a problem in the old way as before, you get a description in the Wigner distribution domain for free by using the formula here. This also means that one can generally apply this trick to any applications. Okay, we stepped through all necessary steps, and now we can apply them to see how we can use them for the null-side imaging problem. For both diffraction propagators, we can calculate capital K from H using skeleton we just talked about. Here, I use a one-dimensional example to display our main result. We consider a scenario where input field is a cross-section of the hidden target, and the output field is also drawn from a line segment. The input and output slides are moving away from each other, try to mimic a target that is moving away from the wall. The exact solution, which is known as Wigner Distribution diffraction, has non-geometric interpretation compared to the approximate solution that can be thought as a shear mapping. In the Wigner distribution domain, it is quite straightforward to see the wavefront propagation. This can generally apply to the process between target and the wall, or it can be used to think how we can form an image from the captured wave. Next, we can study null-side imaging resolution limit. This will work as a guideline for the best resolution we can achieve. We do this by mimicking a point spread function from a regular imaging system. This resolution limit so far will depend on both target distance respect to the aperture size, just like a regular imaging. I'm going to show you reconstructed result for the same checkerboard object with the same scanning area, but varying distance. For reference purposes, I put the calculate point spread function for this virtual imaging system on the right side. Please see how the lateral resolution is degraded as a function of distance. Another interesting thing we found out is that the error between the exact and approximate propagator depends on acquisition stream. This is due to the fact that by sending different illumination wavefront, the virtual illumination field among different acquisitions are different. More details, please refer to our paper. I would like to have all your attentions. This talk did not cover all aspects of phasor field null-side imaging. For example, we have one that is just online several days ago. This paper is about fast null-side reconstruction using Rayleigh Sommerfeld diffraction solver. This paper is also in the poster section. Feel free to have a look. I hope you all can have a picture of what is null-side imaging. For more details, please visit our webpage and related works, and feel free to send out questions. Thank you.
Thank you for the great presentation.
Yeah, thank you.
Perhaps I can start things off by asking a question here. So the Wigner distribution function seems like a really powerful tool for analyzing non-line of sight transport in this phasor field domain. And at the end, you touched on some points regarding resolution limits. Now, there have been some works that are dealing with occlusions that are present, or occluders rather, that are present in that non-line of sight space. I was wondering whether your framework, your analysis techniques here can be used to test what are the resolution limits in that kind of domain.
So if I understand the question correctly, you were saying that can we use occluder to further enhance the resolution limit. Is that correct?
Yeah, so as opposed to just dealing with a wall and objects that are hidden from sight, what if there's an occluder in between? So others have used those occluders in order to encode information about that non-line of sight object on the wall itself. And I was wondering whether this Wigner distribution function technique can be used.
So first, as far as I know, technically for the active time resolved null-side imaging, there is a work trying to use occlusion to enhance reconstruction. By barrier down for a huge computational barrier, what I try to say is the algorithm complexity. In terms of non-transient, basically use a regular camera, there are work try to use pinhole or anti-pinhole to use shadow to decode information. Ideally, what the phase review is a frequency description for the non-side imaging. If you model from an active scenario, you can easily go back to a passive scenario as we show in the video, as a regular imaging problem. And then we are working on trying to use occlusion for the time resolved active scenario. But the challenge was how to, first is, do you know the occlusion specifically? That is the first thing. Second thing is, if you use it as a prior, how do you further enhance the reconstruction? So it is the active further direction we are looking at.
Cool. So reminder, everyone can still write questions into chat, and I'll relay them to the author here. We just had our first question come in from Aditya. He is asking, is there an Abe's diffraction limit based on virtual wave optics? And what is the wavelength equivalent for virtual wave optics?
So yeah, I'm glad people get the idea so quickly. Naively, if you have the capture space and time signal, instead of doing a 3D Fourier transform, you just do a 1D temperature transform and then extract one slice. And then the image outcome was that there is a certain, for the wavefront you sample, even though the illumination you send is a broadband, it contains almost all the light path. Then once you choose a certain spatial sampling rate, for example, if you choose a 1 meter by 1 meter relay wall, clearly how many discrete samples you drop inside this 1 meter by 1 meter relay wall will determine whether for a certain frequency it is undersampled or oversampled. That is first thing to convert from a regular imaging to a virtual imaging point of view, that there is a certain stopping criterion, stop you, because if you go to a shorter virtual wavelength, some of the phase is undersampled, clearly show in the result. And once you choose a wavelength, then the next thing was, what are the resolution limit? It is naturally associated with the amplitude term, because at the end of the day, you want to ask about the resolvability about two amplitude, and they haven't tested that yet. We just use the underlying principle, like asking what are the basic Nyquist rate to sample those resolution limit or the wavefront on the wall. So as we understand clearly from a Nyquist rate point of view, if you have a wavelength, suppose it's 4 centimeter as a sinus wave, varying from positive to negative value, the least amount of discrete point you have to drop is 3 points. So naively means that without asking about anything, you have to have a certain threshold by half lambda to sample those waveforms. Yep.
Okay, I'll ask one last question very quickly here from Akshav. How can interpreting the non-line of sight measurements in the Wigner distribution space be used to develop better and faster reconstruction techniques?
Oh, that is one thing that this is also a common question. So from my perspective, thinking how the signal transform as a picture is more intuitive than just plugging into the equation. So maybe different people have a different taste. But as I said, a lot of people say you can do lots of things that are independent from this understanding. But with that in mind, in our paper, we also, once we do this work, we also realize that compared with different acquisition, those kind of Wigner distribution display, we find out the error for a different propagator depends on acquisition scheme. That is easily just highlighted by how this 2D image is transformed in the space and spatial frequency. And also one can, as I said in the video, you can use it directly for the current forward model. If the model is already packed into a convolution format, you can just use a formula or recipe to see the outcome. But then the barrier was the notation. We will have a rough thought about this. If you have a variable 3, then in general case, the integral will be a function of 6 dimension. And then if you plug into the Wigner distribution framework, you may end up using 24 alphabet, which is a pain in the ass.
Thanks again, Xiaoshen. All right, so our next talk is titled High Resolution Diffuse Optical Tomography Using Short-Range Indirect Subsurface Imaging. This paper won ICCP's Best Paper Honorable Mention Award, so it's one to look forward to. The presenter is Xiao Liu from Carnegie Mellon University. Let's go.
Hi, this is Chao. Today, I'm going to talk about our work on high-resolution diffuse optical tomography using short-range indirect subsurface imaging. This is a joint work of groups from Carnegie Mellon University and Rice University. See below the skin is a very important task, especially for medical diagnosis. Over the years, a broad range of methods have been invented and applied in the clinical procedures. In particular, we are interested in a non-invasive imaging scheme, the diffuse optical tomography, or DOT. The goal is to estimate the absorption variations within the medium due to heterogeneities such as bands or tumor. As a non-invasive subsurface imaging method, the DOT has been adopted in a broad range of applications. Despite of being able to see beneath human skin, traditional DOT has two major drawbacks. First, due to the physical size of each point and detector, the dimension of the whole system is usually very large. The captured data is of much lower resolution compared with an off-the-shelf image sensor, which includes millions of pixels. The second drawback is that DOT is a computationally expensive inverse problem, and it is very difficult to make it scale to millions of point detectors. In this work, we propose a high-resolution DOT imaging system using a pair of camera and laser projector. On top of that, we propose a computationally efficient DOT algorithm that can easily be scaled up to megapixel resolution. As there is no point source or detector attached to the surface, the imaging system is compact and non-contact. Using the proposed system, we are able to reconstruct the 3D structure embedded in highly scattered medium with much higher resolution compared with traditional DOTs. Our method is built on top of DOT, so let's quickly review it. For homogeneous and highly scattered medium, the light intensity at the detector is governed by the well-known diffusion equation, with the scatter parameters on the left and source intensity on the right. When there are heterogeneities, the scattering property change. For tissues, this change is mostly contributed by the change in absorption coefficients. In this case, the change of light intensity due to heterogeneities is governed by a diffusion equation of the same form as a homogeneous case. The left-hand side includes the second-order partial derivative of the change of the light intensity due to the embeddings. The solution to this diffusion equation at the volume boundary is the product between the absorption variation and the phase function, and integrated over the entire volume under consideration. Given the phase function and the change of intensities for multiple source detector pairs, we want to recover the distribution of absorption variations of the volume. However, due to physical dimension of point source and detectors, the captured data is usually of very low spatial resolution. In addition, even if there is no limitation on the physical dimension, since the phase function is different for different source detector pairs, and the integration is over the entire volume under consideration, it is computationally infeasible for high-resolution data captured by millions of source detector pairs. If we replace the point source detector pair with a pair of illumination line and a line sensor, and scan the line pair through the image region, we can get high-resolution image. This imaging scheme can be implemented with a synchronized rolling shutter camera and a projector. In this work, we show that the change of image intensity can be formulated as a 3D convolution between the absorption variation distribution and a kernel function, where the kernel function can be controlled by changing the delay between the source and detector lines. The final measurement is contributed by the homogeneous and heterogeneous components, where the homogeneous component on the right-hand side can either be measured or analytically computed given the scattering properties of the surrounding homogeneous material. The heterogeneous component is formulated as the 3D convolution between unknown absorption variation and a controllable sensitivity kernel. As a result, by using the scanning pair of illumination and sensing line, we get a high-resolution DOT system that captures megapixel resolution data. This is essentially equivalent to the traditional DOT setup with millions of overlapping source detector pairs. On the basis of image scheme, we have an efficient convolutional model that can be easily scaled up to image resolution, since the convolution operation is heavily optimized on modern GPUs. Here, we visualize the normalized kernel for one pixel with different delay settings. As we can see, with larger delay, the non-zero support for the kernel becomes deeper in the side view and larger in the top view. This corresponds to an image scheme with deeper sensitivity but more blurry images. One thing to note about here is that we cannot always keep increasing the delay to get deeper sensitivity. This is because the signal-to-noise ratio will reduce with longer optical distances. Given the measured values, we can estimate the absorption variations due to heterogeneities and the scattering parameters for the surrounding homogeneous medium. This can be done in an analysis by synthesis approach, where we optimize for the variables to minimize the difference between the captured image and the rendered images, plus the regularization term. This is similar to some image deep learning pipelines, where the absorption variation corresponds to the unknown sharp image and the sensitivity kernel corresponds to the blurring kernels. Our proposed system consists of a high-resolution camera and a MEMS-based laser projector. The laser beam from the source is reflected and redirected by the MEMS mirror. We use a red laser centered at 650 nanometers, with a power of 15 milliwatts. The camera and the MEMS mirror are mounted at the same height, so the epipolar lines on the image plane for the camera are horizontal rows. During imaging, we can synchronize the camera and projector such that when one epipolar line or one row on the camera is exposed, the corresponding epipolar line on the projector image plane is illuminated. To capture short-range indirect light image, we add a constant delay between the exposed row and the corresponding epipolar line on the projector image. This results in two synchronized scanning planes. In each short-range indirect image, the image intensity is contributed only by light coming from one epipolar plane to another for the projector camera pair. The projection of the illuminated line and exposed line onto a sample are always parallel during one scan. By adjusting the delay, we can capture the short-range indirect images gated by different optical lengths. We show the stack of images showing on the right, captured with increasing delays. As we can see, the local contrast of the objects becomes more obvious as delay increases, because the non-zero support for the sensitivity kernel becomes deeper. On the other hand, the overall brightness of the image decreases because we are capturing images gated with longer optical lengths. As a result, there is no free lunch since we have to compromise between the sensing depth and signal-to-noise ratio. We compare the image captured by our verge setup and the frontal parallel setup with no vergence angle. The images are captured for different regions over the body. As we can see, with the verge setup, the object can be placed much closer to the camera without going out of view for the projector and cannot be illuminated. As a result, more fine-grained details are visible. Getting finer details for structures underneath skin is important for applications such as skin disease diagnosis, and could be served as a clinical procedure before biopsy for dermatologists to better localize the target region. With a proposed image system and DOT algorithm, we can get high-resolution tomography for structures in highly scattered medium. In the captured short-range indirect image, the contrast of the observed object boundaries are more obvious than those in the regular images. Given the short-range indirect images, we are able to reconstruct the 3D structure up to 8 mm through full milk using the proposed DOT algorithm, even though the object boundaries are blurry in the input images. In summary, in this work, we propose a compact and high-resolution DOT system using short-range indirect subsurface imaging. On top of that, we develop an efficient tomography algorithm that can scale up to megapixel resolution. As a future directions, we aim to see deeper using light source with longer wavelengths. In addition, it is a promising direction to make the capture faster in order to perform DOT on dynamic scenes such as subsurface blood flow. We are also aiming to perform clinical experiments on human patients in order to evaluate the clinical aspects of our system. Thank you for your attention.
Great presentation, Chao, and
Thanks.
great paper as well. I have a couple of questions that I want to start off with, or at least one. So you looked at different spacings between the incident and outgoing illumination. I was wondering whether you also took a look at perhaps rotating the two incident planes on the sample.
Rotating, you mean instead of using the epipolar planes, just rotating the orientation of those two planes?
Yeah, I understand there are going to be some hardware constraints, right? So you're exploiting epipolar geometry, but perhaps you have a second camera that you can somehow exploit. Would there be any advantage to using a pair of cameras where the lines are oriented in different ways?
Yes, I think there would be. So here we assume the isotropic light propagation distribution for dense scatter medium, right? So for some case, such as based on the orientation of the embeddings, also the scattering coefficient of the homogeneous, the distribution may be anisotropic when the dense scattering assumption fail. In this case, the angular information will be useful. And say using another, like you can rotate by 90 degrees with another camera will help in this case.
Okay, cool. All right, we have a question from Keenan Deng. He was asking, he's wondering, how do you find the optimal delay between the projector and the rolling shutter?
So we try a set of optical delays. So instead of capturing one single short-range indirect image, we capture a set of indirect images with different delays. And the range of the indirect images, the delay is up to 10 millimeters between the two planes, the illumination plane and the camera plane. And
so, sorry to jump in there. So is the 10 millimeter range, you found that experimentally, or is there some way to justify that range?
Okay, so we'll try longer ones because, as I said in the presentation, longer separation will have deeper sensitivity. But we find out that you can try like more, say more than like 20 millimeters, then the SNR ratio of the image will be pretty low. As a result, we have to capture higher quality HDR images that will increase the capturing time. So at last we try 10 millimeters and found out that that works.
Right, sounds
for
good.
like up to 8 millimeters inside the whole milk.
Okay, we have another question from Ingletu. My apologies for butchering that name. Can time gating be used to further improve reconstruction resolution?
Of course, yes, of course. So this, I think our method can be classified as light distance gating, right? So light distance is between the two planes. And in each short range indirect image, it only gets the light from one plane to another, right? So if we use the time gating, that would be a more straightforward, like you say, using a space sensor, and it would be more straightforward. And I think that would be more information included. Yes.
Great. Okay. Unfortunately, we can't get to all the questions. We'll have to move on to the next talk. Thanks, Chao.
Thank you.
So the next talk is titled Simulating Anisoplanatic Turbulence by Sampling Correlated Zernike Coefficients. The presenter is Nicholas Schmidt from Purdue University. And let's get started.
Hi, my name is Nick. I'm a student at Purdue University in the School of Electrical Engineering. And today I'm going to be talking about simulating anisoplanatic turbulence by sampling intermodal and spatially correlated Zernike coefficients. First, we'd like to begin with addressing why a turbulence simulator is needed. One motivating factor is the use in evaluating reconstruction methods in order to have some ground truth to compare against. In addition, generating data for deep learning approaches is needed, and as most approaches true to the theory are slow, we'd like something a bit faster. Some methods compromise accuracy for speed in order to meet this need, and therefore the desire of fast but accurate simulators is in high demand. The goal of this work is to design a fast, open source, and accurate atmospheric turbulence simulator. This is achieved through a realization of the approximate equivalence of two bodies of work, which allows us to reduce the problem to a sampling problem. So to begin, let's take a look at the background and then related work. We are primarily concerned with what happens as light propagates through the atmosphere. In a vacuum, a pulse of light will originate at the source and spherically propagate outwards until it eventually lands on our aperture in red. Since we are typically talking about long ranges in this work, as is the case with most turbulence works, we can consider the wave to arrive at our aperture roughly flat. In a vacuum, we then have no phase distortions and get a resulting diffraction point spread function. When we introduce randomness into the atmosphere, we get random pockets of different indices of refraction, which will cause distortions in our wave. An easy way to visualize this is to divide the atmosphere into chunks and let the wave propagate through, becoming dented by the representative phase screens. When it eventually arrives at our aperture, what would have been flat is now dented up and distorted, and produces a point spread function, something like what we have shown. There are two principal effects here: blur, and something we highlight with the red arrow, tilt. Another convenient thing about the phase screen perspective is our spatial correlation with another light source is straightforward, as they will share overlapping portions of the screens. Now we'd like to put our approach into context. The phase screen approach is the most commonly used in practice, referred to as split-step propagation, as it goes back and forth between phase imparting and free space propagation, thus splitting the steps. A difficulty here is that it is computationally expensive. We'll have to take as many forward and inverse Fourier transform pairs as there are phase screens, which is typically around 10. Furthermore, we'll have to do this for roughly every pixel in the image. Propagation-free methods also exist and primarily focus on the tilt effects and impart some spatially invariant blur. While these are fast, they are not necessarily accurate to the theory, specifically with respect to the blurring effects. Other approaches include geometric optics perspectives, such as ray tracing, or empirically driven methods such as sparse representation. This work fits somewhere in between split-step propagation and propagation-free methods. Now onto our method. For our approach, we like to collapse the phase screens using the thin screen model and get directly to the phase in order to avoid the Fourier transforms. Doing away with the phase screens, however, leaves us with a bit of difficulty in evaluating their spatial correlation. We use a set of basis functions known as the Zernike polynomials, as suggested by Knoll in 1976, to represent the random wavefronts. Knoll derives the statistics for the coefficients from a single point source as a function of turbulence parameters. The Zernike polynomials also have a bit of interpretation. For instance, the two bases sitting above the red line represent tilt, or approximately the shifting in the image. The others below the line all contribute to the blur. When considering a second point source, the correlation becomes difficult as a function of their angles of arrival. The correlations of the bases above the line are known, but not those below. By using the Zernike polynomials, we introduce another type of correlation, intermodal. That is, what is the correlation between two coefficients from the same point source? Luckily, Null has already taken care of this. Therefore, we'd like to include both types of correlations in our simulator, intermodal and spatial. What we do is to consider the following situation. Say we have two areas we'd like to generate random wavefronts for, shown in blue and yellow. If they were close, we'd like them to be similar, and if they were far away, then different. We can describe this by the angle between them, the angle of arrival. But as we mentioned, this isn't known how to evaluate. What we then do is to strip away everything except for the wavefronts and put them in the following configuration. We then pretend instead that they are two wavefronts arriving at two different cameras, observing one point source and separated by some vector. It turns out that if we write out the integrations and assume a constant turbulence strength over the path, as well as use a first-order approximation, the two correlations are proportional to one another. The link is then established between the angle of arrival correlations from Basu and multi-aperture correlations from Shannon. We may then define the normalized spatial correlation matrices. As explained in Shannon's work, we can then write the correlation of the tilt terms as the following convenient expression, with minus corresponding to horizontal and plus corresponding to vertical. In order to generate the tilts, we notice these are the autocorrelation matrices of the Zernike coefficients 2 and 3, and due to wide sense stationarity, can generate tilts quickly using the power spectral density and multiplication with white noise. Another advantage in establishing such a link is that multi-aperture correlations for all Zernike coefficients are known how to evaluate as a result of Takato. We then plot the spatial correlations as a function of separations and find, as did Takato, the following behavior. That is, the high-order coefficients, those corresponding to the blur, have a very short correlation range, while the tilt coefficients have almost global correlation. We then make the following approximation. For the blur terms, we segment the image into blocks and use only one PSF for the entire block, and maintain the tilt having its global dependence. To illustrate the process of simulation, we first take a ground truth image and generate tilt wavefronts which are correlated across the image. This produces an image that is sharp but distorted by random pixel shifting. We then take this image and segment it into chunks and blur each block independently in order to produce the final image. Now onto our experiments. One set of experiments is to compare with real data from the NATO dataset with known propagation parameters. Ignoring contrast, we see a great deal of similarity in the amount of blur and warping present in both images. Furthermore, we can compare our tilts to a propagation-free method and their chosen parameters. Again, we seem to observe a loose sense of similarity. However, we'd like to motivate that these comparisons alone are not convincing, and that we have known statistics to compare to. Therefore, the next two experiments we find much more informative. The first experiment we perform is the spatial tilt statistics as a function of pixel separation. Between our approach, the multi-aperture correlations, and the angle of arrival correlations, we find a considerable match in both the tilt correlation and their differential tilt variance. The next experiment is comparing the temporal behavior of our generated PSFs with the theory. We can average over the PSFs and obtain the empirical long exposure PSF, as well as average over the centered point spread functions in order to obtain the empirical short exposure PSF. We again find the match between simulation and theory. To summarize, A propagation-free simulator with correspondence to the known statistics is proposed. In addition, a way to evaluate these spatial correlations is introduced through an equivalence between angle of arrival and multi-aperture. We expect this to be useful in the generation of large amounts of training data and the standardization of evaluation of reconstruction methods. Thank you.
Great. Thanks for the talk, Nick. So perhaps I can kickstart some questions off here. So
Sure.
Your work, you assume that your objects or the sources are at some plane infinitely far away. Is that correct?
Yeah, correct. To give you maybe an idea, maybe about 7 kilometers or something like that would be a reasonable distance.
Is there a way to take into consideration the geometry of a scene? So if you're dealing with objects that are perhaps closer, there's objects that are close by, objects that are further away, they would experience different amounts of turbulence. Is there a way to extend your work for dealing with these scenes?
I mean, that's really a great question. I would say that there certainly must be a way to do that. I would say most works probably assume some sort of, like whatever you're looking at, you can assume is roughly at the same depth, although I can certainly see some sort of depth map, and then kind of attenuating your propagation distance, being a very reasonable sort of addition to something like that, and any other really work, such as split step or something like that.
Great. So we have a question from our audience, our virtual audience. So Surin said, great talk. Is there a way to extend this for temporal correlations? So multiple frames through the same turbulent media, or is it solely for spatial correlations?
Yeah, that's a fantastic question. Again, that to maybe refer back to split step, because I think it's a bit more easy to visualize with the split step where you have the discrete phase screens. In that case, what they do, one approach that they do is they'll generate a much bigger phase screen than they would need, and then they slowly shift it across. And that's how they get their sort of temporal evolution of the point spread function and also maintaining their spatial correlation. So for this, what we'd have to do is, for instance, in your covariance function, you'd have to assume, well, one, you'd have to know your temporal sampling rate or something like that. But also you'd have to assume some sort of mean velocity term. And by that, I mean just how quickly that phase screen is dragging across. That is something we'd like to do. I think we're wanting to be a bit careful about doing it. One, it would be this sort of three-dimensional covariance matrix. But in addition, it's a bit of a debated topic as to how that mean velocity term should be handled. I mean, what the value should be. It's a very much kind of debated thing. So we should want to be careful with that going forward. But there must be some way to do it. And that is something we look forward to doing in the future. Fair.
Great. Thank you for the talk once again, Nick.
Yeah,
the final talk for ICCP is titled Towards Reflectometry from Interreflections. So the lead authors for this work are Kfir Shem-Tov from Technion and Sai Bangaru from MIT. Sai will be presenting this talk today. Take it away.
Hello, everyone. I will now present our work on how interreflections can be helpful for reflectometry. By reflectometry, we refer to the process of acquiring the reflectance properties of real-world materials as represented by their bidirectional reflectance distribution function. These measured BRDFs can facilitate a variety of applications such as interior decor, industrial design, VR, and AR, where there is an increasing demand for photorealism. In its most general form, the BRDF is a 4D function representing the amount of light a surface reflects for any combination of incoming and outgoing directions. We will discretize this function and visualize it as a 2D matrix for convenience. Probably the simplest reflectometry procedure is to use a Gonier reflectometer. We use a laser and a camera to image a flat material sample from all different combinations of incoming and outgoing directions. Each intensity measurement directly maps to a BRDF entry. Unfortunately, this exhaustive acquisition procedure requires a very large number of measurements to accurately represent the BRDF. It is also possible to modify the acquisition procedure in order to multiplex information about multiple BRDF entries into each image measurement. This can be done by using a curved surface with many normal directions, or by using complex lighting patterns such as spherical harmonics or frequency domain lighting. All of these techniques effectively measure a cross-section of the BRDF with each captured image. While this is more efficient than exhaustive sampling, it still requires capturing potentially hundreds of images. What all of these techniques have in common is that they inherently assume the measurements to be the result of single bounce light transport. Between leaving the light source and reaching the camera, all light paths only reflect once on the material surface. Fundamentally, this assumption allows us to map measurements to BRDF values either directly or at most by solving a simple linear system. Qualitatively, we can categorize reflectometry methods on a spectrum that trades off number of measurements with computational complexity. In this spectrum, existing methods almost exclusively occupy the left side. This motivates the following question. Can we devise a reflectometry method that is on the other end of the spectrum, allowing high fidelity BRDF recovery from very few measurements at the cost of increased computational processing? Our main goal in this work is to show that this can be achieved by moving away from single bounce assumption and taking advantage of interreflection effects. For some insight, let's say we use a concave shape for reflectometry. Each image measurement will sum contributions from not only single bounce paths, but also from two bounce and higher order paths. The contribution of a two bounce path will be a function of two entries of the BRDF, one for each reflection event. A three bounce path will involve three entries of the BRDF and so on. Consequently, just a single image can provide us with information about a very large set of BRDF entries. However, the relationship between measurements and BRDF values is highly nonlinear and can no longer be trivially inverted. In the rest of this talk, I will show you how to overcome this obstacle in order to make reflectometry from interreflections possible. I will first discuss an analysis by synthesis framework that uses differentiable rendering to solve for BRDF representations from a single image containing higher order transport effects. I will show simulated experiments where we combine this framework with a suitable BRDF parameterization to recover high fidelity BRDF measurements. Finally, I will discuss how to quantify the effect of shape on the quality of the BRDF recovery. Our measurement setup is fairly simple. We capture a single image of a surface of known shape using calibrated directional illumination and an orthographic camera. We then perform analysis by synthesis. We search for a BRDF that, when used with a simulator, can reproduce the measured image. Given as input the calibrated scene parameters and the BRDF hypothesis, our simulator must be able to reproduce the high-order transport effects present in our measurements. Additionally, to enable efficient optimization of the highly nonlinear loss of analysis by synthesis, the simulator should also compute derivatives of images with respect to the BRDF. We achieve both of these objectives by using a Monte Carlo differentiable renderer, which we have implemented on top of the bidirectional path tracer of Mitsuba. We can now turn our attention to the next component of our analysis by synthesis framework, the BRDF representation. The non-parametric 4D form of the BRDF, while very descriptive, can be unwieldy for optimization. Instead, we want to use a more compact but still descriptive BRDF representation. We adopt a linear basis parameterization that has been common in the reflectometry literature. For this, we select a set of basis elements, each corresponding to a valid BRDF. Then we can approximate any unknown BRDF as a linear combination of these basis elements by recovering the mixing weights W that produce the closest match to image measurements. For our basis, we use 40 BRDFs computed to best fit the Merle database. A key point here is that for a non-convex surface, images rendered with each of the basis BRDFs do not mix linearly. This makes it necessary to use Monte Carlo differentiable rendering to optimize for the mixing weights. Let's see some results. We begin with a simple example that demonstrates the rich information that can be obtained by using interreflections. We consider a tetrahedron, imaged with an orthographic camera and a directional light source. As the tetrahedron has only 3 visible faces, the captured image will be the result of reflection at only 3 angles, and will provide us with only 3 constraints on the BRDF. We additionally consider the concave side of the same tetrahedron. Thanks to the paths that reflect multiple times at its interior, a single image in this case will provide us with significantly more constraints on the BRDF. To quantify this, we use our optimization framework to recover a synthetic material represented using bases with different numbers of elements. When our basis has 3 elements, and therefore our BRDF has only 3 parameters, both convex and concave shapes provide sufficient constraints to correctly recover the unknown BRDF. However, as we increase the number of basis elements, the convex case becomes under-constrained and the BRDF recovery is unsuccessful. By contrast, in the concave case, the BRDF recovery remains just as accurate even when we increase the number of atoms to 5, 10, or even 40. In practice, instead of a tetrahedron, we would use a more informative shape for reflectometry, such as a sphere. By having a different normal at each surface point, a convex sphere provides us with many more than 3 constraints on the BRDF. Even in this case, the concave sphere provides still more information about the BRDF thanks to the interreflections. We can quantify this by comparing the BRDF reconstruction accuracy achieved using a single image of each of the two shapes. In the results that we show, the unknown BRDF comes from the MERL database, and we visualize both the ground truth and the two recovered BRDFs by rendering the images of a common shape under environment map illumination. Using the concave sphere improves single-shot BRDF parameter recovery by approximately 6.3 times across the entire MERL dataset when compared to the convex case. As we can observe from these results, what shape we use has a strong effect on the accuracy of BRDF recovery. This motivates two important questions. First, how can we systematically characterize how informative each shape is for reflectometry? And second, how can we design an optimal shape that maximizes the amount of information on the unknown BRDF available in a single image measurement? In the rest of the talk, I will show some first steps that we have taken towards answering these questions. To simplify analysis and visualization, we will adopt the so-called bivariate representation, which expresses a BRDF as a function of only two angles theta h and theta d defined as follows. Consider the vectors omega in and omega out representing the incoming and outgoing light directions. The half vector h is the direction vector corresponding to their bisector. The angle between the half vector and the normal vector is theta h, and the angle between the omega in and omega out is theta d. We can use the bivariate representation to visualize BRDFs as 2D matrices. We show this for two example BRDFs along with the representative images rendered with these BRDFs. In each table, the top part corresponds to near specular reflections, with the top left region being near normal incidence and the top right region being grazing incidence. We can use the bivariate representation to visualize which parts of the BRDF are being sampled using different shapes. Let's look at the convex and concave tetrahedra we considered earlier. If we consider only single bounce paths, then both shapes sample only 3 entries in the bivariate table corresponding to the 3 visible faces of the tetrahedron. However, as we consider paths with more than one bounce, we see that the concave shape samples a much larger part of the bivariate table, providing a lot more information about the BRDF. Now let's consider the convex and concave sphere shapes. Single bounce paths only sample one column of the bivariate table corresponding to the constant theta d angle between our fixed illumination and viewing directions. As before, when we consider paths with more than one bounce, the concave shape allows us to sample a much larger part of the bivariate space. We note, though, that even the concave sphere cannot sample the part of the bivariate space corresponding to specular reflection at normal incidence. This motivates the question, can we design a shape that improves the coverage of the bivariate space? We show one simple procedure for producing such a custom shape through two design goals. First, we want our shape to provide strong coverage of the specular part of the bivariate space. This is the part where we expect the BRDF to have high and rapidly changing values, and thus has a dominant effect on the appearance. Second, we want this coverage to be achieved through paths of no more than 2 bounces, as higher order paths will have smaller contributions to the overall image. To simplify our design procedure, we assume that the incoming and outgoing directions are the same. We start off the design of our custom shape using a half sphere, which helps maximize the coverage from single bounce paths. We design the rest of the shape as follows. For any given ray from the camera, taking into account our first design goal, we consider its specular reflection on the half sphere. The reflected ray will intersect the unknown part of the shape at some point where another reflection will occur. We know that the resulting ray must go towards the light to form a 2-bounce path. Finally, from goal 1, we select the unknown normal at this point to correspond to the mirror reflection. Repeating this process for all camera rays gives us a set of normal constraints. By integrating these normals, we can form a final shape that is shown here. We can use the same bivariate representation as before to visualize the information our custom shape provides for reflectometry. Compared to the concave sphere, we observe that our shape achieves much more uniform coverage of the bivariate space, including coverage of the top left specular part. We can also perform simulated reconstruction experiments to see how this improved coverage affects BRDF recovery quality. We show single-shot recovery experiments for a few BRDFs from the MERL database. Using our custom shape, we can achieve 11.2 times more accurate BRDF recovery than when using the convex sphere, and 2 times more accurate recovery than when using the concave sphere. To conclude, let me summarize a few key takeaways from our paper. First, we have shown that higher order transport effects can provide rich information for reflectometry, allowing us to significantly reduce the number of image measurements required. Second, we have shown that the combination of analysis by synthesis with physically accurate differentiable rendering can help us solve the very nonlinear inverse problem required for recovering the unknown PRDF. Thirdly, we have highlighted the important effect different concave shapes can have on the PRDF reconstruction quality. We have shown how to design one kind of shape that is well suited for reflectometry, and we hope that our work will motivate significant additional research on discovering optimal shapes for this application. Thank you for your attention. Please visit our website for code and additional results.
Great, thanks, Sai. We already have a couple of questions in chat, so I'll start with that. So Mian Wei asked, could you have a case where the choice of setup, so position of light source and camera relative to the geometry and relative to each other, changes what shapes are optimal?
Absolutely, yes. So for the design of our custom shape, we've assumed that the lighting and camera are both orthographic directional and pointing in the same direction. Changing this will definitely change what shape is optimal. So that's an open problem that we wanted to pose. Is there a framework that you can design that will automatically optimize for the optimal shape depending on the lighting and the camera conditions? So that's a valid question, but like I said, it's a bit of an open problem. So we've just given one possibility, and then yeah.
I'll piggyback on that question a little bit as well. So I was wondering, did you think about using structured illumination in addition to optimizing shape and in order to solve this reflectometry problem?
Structural illumination, well, we did think about it, but I think in our experiments that we provided, we've only used the photometric setup because that's where we started from. So in the photometric setup, we just assumed directional illumination. But because our method is based on a physically accurate differentiable rendering algorithm, we base it on Mitsuba's BDPT. So any light source that you can model in that system will work. I think the main reason we decided to go with the photometric model is that it's easier to calibrate if we wanted to get real life measurements.
Yeah, that makes sense. All right, another question from the chat from Dennis Denbrock. He said, very interesting idea. How does your work compare to that of Nielsen et al.? So optimal BRDF sampling, or the paper titled Optimal BRDF Sampling.
I think off the top of my head, I don't remember exactly what the papers do, but there are quite a few papers which try to import and sample BRDFs. We haven't quite considered how that would work because it's hard to, in the single bounce case, you can sort of reason about what's the optimal way of finding samples for BRDFs. But once you consider interreflections, you can see that it's much harder to know which directions give you the best, give you the most intensity. So that is also something I would consider as an open problem, and I feel like we can't directly compare the two because of the way in which we're considering samples. Our idea is to significantly reduce the number of measurements in order to capture a much larger, several measurements from a much larger space of the PRDF.
Great, thank you. Unfortunately, we're gonna have to wrap it up for this session. So thank you once again, and let's have a virtual round of applause for all the authors and thank them for their great presentations. If you have any additional questions, I already see some in the chat. Feel free to ask them now, and the authors will try to get to you as soon as possible. And before concluding this session, I want to remind everyone that we have a poster and demo program. Check that out. Voting for best poster and demo closes at 4 p.m. Central Time. So that's in half an hour. So get your votes in on time. Also, in a little bit, 5 p.m. Central Time, we'll have closing remarks, and we'll also be announcing the Best Poster Demo Award then. So be sure to attend. Thank you, everyone, for tuning in, and we'll see you later.